And so we saw that a lot of your research is about making or putting magnetometers in interesting places and understanding the data that comes out of them. So what is it that you do? For example, do you design the actual magnetometers themselves, or do you find interesting places to put them and new ways to extract data? What does a space scientist do on a daily basis, or someone like you?
So there's a lot of different ways to measure things, including magnetic fields. And the classic space-based magnetometer, it's called a flux gate magnetometer. So pretty much every magnetometer that has flown on Galileo, on Cassini, on almost all of the Earth orbiting spacecraft are flux gate magnetometers. And so they've been around in space longer than I've been on Earth, so the last 60 years. And as we've developed our capabilities in electronics, they've continued to shrink and shrink and shrink and have low power. But one of sort of the key scientific or engineering innovations is if you can reduce a parameter by an order of magnitude or increase it by an order of magnitude. So if I'm a telescope builder and I can collect 10 times more light, or I can have 10 times better resolution, that is a huge advance, and you're going to win a lot of prizes or become really rich. Or if you're an automotive designer and I can increase fuel efficiency by 10 times, so 400 miles per gallon or whatever, right? So order of magnitude is sort of these big jumps. And for electronics, they often call what you're trying to do is reduce swap C, size, weight, and power plus cost. And so if you think of your computer, we've had this thing called, described as Bell's law. So essentially you had building size computers, and then room size computers, then desk size computers, and lap size, and then pocket size with our phones. And now we're going to little microcontrollers that are the size of a pinhead. And once they get that small, you can think about Internet of Things. I can have smart cities where everything is a computer or a sensor communicating with each other. And so now we have this huge network. And so what I've been doing over the last 8 years is trying to take advantage of this mobile phone revolution. For the last 2 years, over 1 billion smartphones have been sold. And so there's a magnetometer, there's accelerometers, there's gyroscopes, there's GPS receivers, there's Wi-Fi antennas, there's Bluetooth antennas and transmitters, there's cellular cameras, microphones, right? There's a ton of sensors, thermometers, and somebody made 1 billion of them. And so it's because the costs and size and power have really shrunk. And so the magnetometer that's in your phone is really crappy in terms of scientific resolution, the smallest field or the smallest change of magnetic field, but it's revolutionary. We actually have a model, in your phone, the world magnetic model. And so your compass, your magnetometer, now helps your Google Maps have a little blue headlight. So your blue dot shows you where you are from GPS, and the headlight shows the direction you're facing, because there's a GPS that tells you your latitude and longitude. And so then you know your declination of the magnetic field between true north and north, and they can figure out exactly where you're, so you can do Pokemon Go and know what you're looking at. But these guys are less than $1. And so a fluxgate magnetometer for a spacecraft is over $1 million. And so if I can say, I can build a space-based magnetometer for 100,000, that's an order of magnitude, then I can start thinking, well, I should have a magnetometer in every spacecraft. And that's what I've been trying to do. And so the last 8 years, I've been working with a company in California called P&I that makes a chip-based magnetometer. And it uses a new type of technology. It's called magnetoinductive. And it's essentially a little circuit, LR circuit, a inductor resistor circuit. And if you remember from your physics class and your Kirchhoff's laws, that all these LRC circuits have time constants and depends on the values of the different components. And you can essentially, every piece of electronics is some combination of inductors, capacitors, and resistors in series or parallel. And we have computers and all types of things that we can measure. And so we've been trying to improve the sensitivity of these magnetometers to become research quality. And in the last few years, we've made really big strides. And so recently, last year, we were selected by NASA to participate in the NASA Artemis Lunar Gateway platform. So the Artemis program is NASA's effort to have the first woman and next man on the moon. So the original goal was 2028, then it got moved to 2024, and it probably get moved back to 2028 because it's hard. It takes a lot of effort and money to do it, but they're launching Gateway, which is going to be a lunar orbiting space station. So it'd be like a mini ISS, but in lunar orbit. And it's going to have a huge ion electric propulsion system. So it can sort of essentially raise and lower its orbit around the moon, depending on if it's going to be picking up Orion crew capsules from Earth, or is going to be dropping down rovers or whatnot onto the surface of the Earth. And we're going to use it as a solar wind monitor. So we're going to be putting energetic particle and plasma and magnetometers on it so we can help predict space weather for the astronaut in the moon.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.